In this Calculus 3 tutorial, I want to use this function to show you that partial derivatives, they behave very strange compared to the good old Calculus 1 derivative when we just have one single variable. Let's have a look. So this is our function. Notice when x, y is not at the origin, we do this. When it's at the origin, we just get 0. Based on this, we'll show that the partial derivative of f with respect to x at the origin is 0. Likewise, for the y, we also get 0. So you can see that we have partial derivatives. However, the function itself is not differentiable at the origin. So we have partial derivatives. We don't get a usual derivative. Yeah, be really careful. Let me do this right here first. And I'm not going to use the quotient rule because one, this is a piecewise function, and two, 0 into x and y, most likely we run into trouble when we just do the computation. So we will use the definition. So partial of f with respect to x at 0. So the idea is that x is the variable and y is the constant. So keep that in mind. Here we take the limit as h approaching 0. We are just going to be doing f of 0 plus h, comma 0, and then minus f of 0, comma 0, and then all over h. So this is going to be the limit as h approaching 0. So this is just h in the x component. I put that in here. So we get h, and then 0 for the y. So multiply by 0, and then continue h squared plus 0 squared. And now this right here is, by default, that's equal to 0. But you can see this is just 0 minus 0. Work this inside out. 0 on the top divided by h. So we get the limit as h approaching 0 of 0. And the answer is equal to 0. So the partial derivative at the origin with respect to x is 0. So this right here checks. And you can see that this is going to be pretty much the same thing. So I will leave that to you guys. That will also give you 0. Now, how are we going to show that the function itself is not differentiable at the origin? The idea here is that having the partial derivative is not enough because we only have the x direction and also the y direction. If you want to have the derivative at the origin, right, for the function to be differentiable, you need to consider all the possible directional derivative. Okay, so how can we show this though? Let's think about the things that we did in Calc 1. How can we show a function that's not differentiable without doing computation? Because most likely the computation will be pretty hard. The answer for that is, if we can show that the function is not continuous at the origin, then we can show that the function is not differentiable. That's the idea. So to show that f is not differentiable at 0, I will say it suffices to show f is not continuous at the origin. So how do we show a function is not continuous? Well, the value of the function at the origin is equal to 0. We will just have to check the limit of this thing when xy is approaching the 0. If the limit does not equal to the value, then the function is discontinuous. That's the key. So we will have to check the limit as xy approaching the origin of our function here. And since xy is approaching the origin, that means x and y, it's not exactly 0. So we'll be using the top expression here. So we just check this thing right here. Now, most likely because we are going to show that f is not continuous, so the answer is not going to be 0. Most likely we have to show the limit doesn't exist. And to do that, we have to come with two different paths, right? So let's go ahead and do it along the x-axis, which is just y equal to 0. So you're just plugging 0 into the y, and then the x stays. So this right here becomes the limit as x approaching 0, x times y is now 0, x squared plus 0 squared. So this is the limit as x approaching 0. The top is 0 over x squared, so the whole thing is 0. So you see that we get 0. Okay, we need another path. This one, we cannot use x equal to 0 because we will have the same result. We don't want that. We want to have a different result. So what do we put? Here, I kind of want the bottom to be the same so that they can be combined. So how about let's do along y is equal to x. So it's just a diagonal. And this thing, when x y approaching 0, 0, it works. So this is going to be the limit. I will keep the x because I'm assigning y to be x. So x is x, y is x now, over x squared plus x squared. Then this is the limit as x approaching 0. The top is x squared. The bottom is 2x squared. Cancel, you get 1/2. The limit as x approaching 0 of 1/2, you get 1/2. So as you can see, these two limits are different. That means this limit does not exist. If the limit does not exist, how can it be equal to 0, right? And now this is what I'm going to write down. I will say, since the limit of our function, when x, y is approaching the origin, do not write this down because this is just a part of the function. We are going to write that down. This is our function. This is not equal to the value of the function as 0, 0, because this right here is 0, and the limit here is really bad, it's D and E. So the limit does not equal to the value. That means we can say f is not even continuous at 0, 0. If it's not continuous, don't even think about differentiability. So that's the conclusion. Be really careful. Sometimes we can have partial derivatives, but the function itself is actually not even differentiable. So how do we check if a function is differentiable or not? We will have to use the definition, and I will do that in that video for you guys. Go ahead and check that out.